In this section 4.9, we are going to talk about the antiderivative. And as you imagine, to do that, we're basically going to go backwards from our derivative. So let's just start with deriving three very simple functions just to kind of get the concept down. So clearly the derivative of f of x equaling x squared plus 1, and again, three simple ones, you know this, 2x, 2x, 2x. So when you take the derivative of all three of those functions, their derivatives are all exactly the same. And we see that because the original functions, f of x, g of x, and h of x, only differ by a constant. So if we were to sketch those three functions and our derivative, so let me draw our derivatives in different. So we'll do f of x equals x squared minus 1. Well, that's going to be a parabola down here, right? G of x equaling x squared is going to be a parabola directly at 0. And h of x, so this is g of x. Let me just identify them. This was our f of x function. And the last one, we'll do it in pink, I guess, the only color I could find. And we'll call that one h of x, which is x squared plus 2. So technically three different functions, three functions that differ only by the constant, all have the derivative of 2x. So f of x equals 2x. That's going to be a steep linear equation because it has a slope of 2. Now, I want to introduce the terminology for an antiderivative, the definition. Antiderivative is defined as a function, we call it capital F, is an antiderivative of f on an interval I, provided the derivative of f equals our f of x. For all x in I. So if my original function now becomes 2x, the antiderivative of that function would be x squared with various constants, because it could be, well, x squared minus 1, it could be x squared, it could be x squared plus 2, so we say it's x squared plus c. And this f of x represents a family of functions that have f of x equaling 2x as their derivative. And in fact, every possible antiderivative of 2x belongs in that family. We have 3 examples here, but as you can imagine, there are infinitely many x squared plus c functions where c could be any number from negative infinity to infinity along that would belong in that family of functions. Now, another name, another notation we'll use for this family of functions is the indefinite integral. So the indefinite integral, it kind of looks like a squished out S, and we're going to talk a little bit more about this symbol for integration in the next chapter, but for now, you're just going to know it as the indefinite integral. The symbol is integral of our f of x dx. This dx piece, again, I'll talk a little bit more about that piece in the next unit, but for now, it basically tells you what you're integrating with respect to. So if we were to integrate f of x with respect to x, this whole thing is called an indefinite integral, and it is equal to that antiderivative plus c, because as we see, there's going to be more than one, so it's equal to that family of functions. So now what we need to do is focus on how to find the antiderivative. So let's think about that for a minute. Well, let's go to our x squared. And let's think through for a second the power rule. Power rule for x squared. And think through the actual steps that you did. You multiplied by the exponent. Right? And then you reduced the original exponent by 1. In that order. Well, I want to reverse the order. So let's call this, and this is a term I am making up, the anti-power rule. To do the anti-power rule, you kind of have to go backwards. And of course, this one's resulted in just 2x. So, to go backwards, well, I now want to do my list of steps this way. So I want to, instead of reduce by 1, what's the opposite of reduce by 1? Increase exponent by 1. So it becomes 2x plus 1. And then instead of multiplying by the exponent, I'm going to divide by the new exponent. So now I have 2x squared, my new exponent's 2, divide by 2, and what am I left with? X squared. I just undid the power rule. Now, of course that's not going to work for everything, but it is going to work for our power rule, and we know we utilize the power rule a lot. So, putting those things together, we have the power rule for indefinite integrals, which says the indefinite integral of xp. Remember that dx tells us what we're differentiating with respect to. Because even though we have done so much differentiating with respect to x, you saw a little bit in the last unit, and you'll see this a lot more as you head into Chapter 6 in Calc 2, you can differentiate with respect to any variable, okay, to y and to other variables. So that piece is important. So what would that look like? Well, it's going to look like my x to the p plus 1 divided by whatever that p plus 1 is, plus c. And you will go through in 4.9 using the different notations. In other words, you will use just the capital F notation, and you will also utilize the indefinite integral notation. So let's just look at a couple quick little examples here. Okay, so here is an indefinite integral with respect to x. Do note when integrals are written, the entire function f of x is in parentheses, so the whole thing is being differentiated with respect to x, not just the last term. You will see that often, and you should utilize that when you are writing integrals. Okay, so I'm going to make one quick adjustment. Because it is much easier to work with our powers and instead of our radicals. Now, there are simple rules that say the integral of the entire sum is equal to the integral of each piece. In other words, you can, because these are being added and subtracted, cannot do it with multiplication and division, because 3x squared is being added to 2, then subtract 5x. You can treat each term individually and apply that anti-power rule to each individual term. So let's do it. Our 3x becomes 5 plus 1, and we're going to divide by 6. Notice constants no longer go away, because think of what made a constant when you took a derivative. Like 2x became 2. So obviously 2 is going to become 2x. And why does that work? Because you're technically doing 2. This right here is x to the 0. So it's 0 plus 1 divided by 1. Now, you don't have to go through that, but I want you to understand that the power rule is still being applied there. Any constant is simply, after you integrate it, going to have an x attached to it. And then 5x, so now we have 1/2 plus 1. And you all know 1/2 plus 2 over 2 is 3/2, divide by 3/2. And then don't forget to add c. So we're going to clean this up, of course. This is going to give us x to the 6 over 2 plus 2x. Another thing you'll get used to as you're doing these integrations and you end up with a lot of fractional exponents, division of 3/2 is the same as multiplication of 2/3. So make sure you apply the correct algebra when simplifying. And we keep our exponents in fractional terms if we have them. And this is what our antiderivative of 3x to the 5th plus 2 minus 5 radical x looks like. A couple things to note. If you have and throughout the rest of this course, and more specifically through the first half of your Calc 2 course, you're going to learn all sorts of rules to help you integrate certain functions. For this particular problem, because our denominator is a single term, it is a lot easier to start off by separating that. Apply the algebra to manipulate it into something that you can easily take the integral of. So I split it up and then simplify each one. 4x to the 19 over x squared is 4x to the 17. X to the negative 8 over x squared, negative 8 minus 2, that's negative 10. And then you can go ahead and apply those power rules to each one. So we have 4x to the 18th. Remember, you got to go up by 1. Be careful when dealing with negatives, please, because when you take negative 10 and you add 1 to it, it becomes negative 9. And just try to clean it up the best you can. 4 out of 18 reduces to 2x to the 18th over 9. Those two negatives make a plus, and we would leave that as 5. X to the negative 9 over 9. Okay, you can put that together as one fraction if you wish. There's a different acceptable ways to write that answer. You can certainly write 2x to the 18th plus 5x to the negative 9 over 9. You can move the x to the negative 9 to 9x to the 9th in the denominator, but we can leave it like that for now. And another quick one, just to remind you of what you can and cannot do. These are two products. So as of now, you do not have a rule to integrate products or anything. So in this case, it is much better to simply work out those products and make that 2z cubed minus 5z squared plus 2z minus 5. And then go ahead and just apply that power rule. 2z to the 4th over 4, 5z cubed over 3, 2z squared over 2. And remember, if there's nothing there, it gets that z. Don't forget to add your c, and always, as best you can, clean up. And of course, these also apply to our trig functions. The difference is you are now looking for the integral. So a couple quick examples. And you have to ask yourself, what function has a derivative that is secant squared? Oh, that's tan x plus c. You do not apply your power rule to that particular function. I'm sorry, I forgot the x. And if you look at your slides that are listed in Canvas, you will find all of your trig functions listed. Not all the trig functions listed, but you will find those derivatives with an integral sign. So for example, secant squared equals tan. We would know that the derivative of the integral of cosine x dx will be sine x. All right, the integral of, say, secant x times tan x dx. Well, you have to think again which trig function has that. That's just secant x. So to know your integrals, you kind of have to know your derivatives really well because you're simply just moving backwards. So let's finish this one out for a minute. Well, you can do them separately. The integral of 2x is simply 2x squared divided by 2. The 3 is your constant, and the integral of cosine is just sine plus c. So it actually equals x squared plus 3 sine x plus c. Now, be careful, though, when doing the integral of sine x. Okay. We know that d dx of cosine x is actually negative sine x. So that means the integral of sine x, well, we need to introduce the negative sign, and the way you do that is just to put it here, and here is actually the opposite of cosine x. So the integral of sine x equals negative cosine x. So just be careful with that. And if you do come across a homework problem where you have trig functions that are more complicated, remember to just utilize your rules and your identities for your trig functions to get them simplified into something you can actually take the derivative of. So as of right now, you cannot do sine x over cosine squared, but you can separate them You can try separating them or just wait. Oh, wait, if I put one of those cosines, right, under sine and leave one on its own, so you just have to start manipulating until you get something that makes sense. This is going to give me tangent, and 1 over cosine is secant. And as we just saw, we know that secant has a derivative of tan x, secant x. So it's simply secant x plus our c. I believe I forgot my plus c up there as well. So there's a lot of different ways. Do note this one. If you try to apply the power rule, let's look what happens, because you're going to come across this and you're going to forget what this integral is, and you're going to try to apply that power rule, which says I simply do x minus 1 plus 1. Well, negative 1 plus 1 is 0. Ooh, yeah. Can't divide by 0. We'll go back and think about it for a second. Hey, what function has a derivative of 1 over x? It's just ln x. So that's one you're going to want to remember. Obviously, e to the x is simply e to the x. One more example. So how do we narrow it down from this whole family of functions? Let's suppose that I want to find, we'll use the other notation, f of x the antiderivative that satisfies the given condition. All right, so let's suppose my f of x function is simply 4 radical x plus 6. But I know when I take the antiderivative to get capital F of x, that just gives me a family of functions. I want a very specific one when capital F of 1 equals 8. So we are going to find the one that satisfies that particular condition. Well, first we've got to find capital F. So going back to our original notation, capital F of x, well, I need to take the antiderivative of 4. That's x to the 1/2. So remember that one becomes 3/2 divided by 3/2. Or multiplication of 2 over 3, if you remember that. And then I need my 6x. And you need some value c. So we got to clean this up before we move forward. So we'll clean it up over here. So that would be 2/3 times 4x to the 3/2. So there's nothing else we can do there. So it would be 8/3 x 3/2 plus but we know, because we are given, let's write given, that f of 1 equals 8. So what we want to do is find the specific function in that entire family of functions that satisfies that condition. So we put in f of 1. Well, that's 8/3, 1 to the 3/2 plus 6 times 1 plus c, and that's going to equal 8. So what do we get? We get 8/3 plus 6. What this will allow us to do is actually to solve for c and come up with the one function from that family that satisfies this equation. We got to do a little bit of work here. C equals 8 minus 6, that's 2 minus 8/3 times 3 over 3, 6/3 minus 8/3 equals negative 2/3. Don't forget to write it. Minus 2/3. And then a very similar problem to that one is what we call an initial value problem. And this is a very, very brief introduction to differential equations, but kind of works the same way. Meaning, suppose we know, that f prime of x is x squared minus 2x, and we had initial value of f of 1 equaling 1/3. So again, all we're doing, it's the same similar type of problem, we're just using different notations. So in this case, you were given f of x as the function and then had to find the family of functions, capital F of x, that have f of x as its derivative. In this case, you're just being told, hey, here's the derivative. So obviously you would then sticking with the same notation, use your antiderivative to find f of x. So of course that's going to be x cubed over 3. And then we get 2x squared over 2. The 2's are going to cancel, so that's just x squared. Still plus c, because we don't know what that constant is yet until we use what we call our initial value. Again, this is just different terminology. We don't call this a family of functions now. We call this our general solution. So differential equations uses this idea, but just use the slightly different terminology. And then to get the specific one, of course, we know that f of 1, which would be 1/3 minus 1 plus c, is equal to 1/3, because we know f of 1 equals 1/3. We're given that information. So we need to go through and solve for c. So c is 1/3 minus 1/3. So it ends up being what? Minus 1/3 plus 1. So c equals 1. Therefore, the solution to our initial value problem is f of x equals x cubed over 3 minus x squared. And now we have the specific function of where c equals 1. So the notation you're going to use is really dependent upon what you're given. You know, if you're given f prime of x and you have to find f of x, it's still an antiderivative. If you're given f of x and asked to find that family of functions, or even a very specific function within that family of functions, you're using the capital F of x function, or maybe you'll be given it in the indefinite integral form. Either way, it is all the same idea of using an antiderivative, which is something we will expand on and work much further with in Chapter 5.